Hi, in this video series we will be discussing mathematical ideas in biology. The purpose of this series is to show that math can be quite illuminating in biology and can help us make some really cool conclusions about animal behavior and nature in general. The range of topics that we will be covering is quite diverse, so we will be talking about the genetics of families, the genetics of populations, regulation and control, like the control of muscular movements in animals. But for this particular video, we will begin by discussing population regulation in separate generations. So let's begin. It is many times the case where the number of animals of a given species in a certain area either remains approximately constant from one year to the next or fluctuates around some intermediate value with some regularity. Now, what we will try to do in this video is model mathematically the change in population numbers. So model population numbers in such a species. Now, why would we want to do that? Well, the goal of this part in the video series, which is the population regulation part, is that we want to at some point be able to represent the factors that can influence the population numbers, and we want to study them. So study influencing factors. Some good things that we can study are predator and prey relations, or even cases of when a certain species is infected with a parasite. So how would that change the population numbers? But we will get to that in due time. Suppose there is a species of animal which has only one breeding season. So one breeding season, for example during summer, and suppose that the adults in this animal species, I will represent them like this, suppose that the adults who breed in one breeding season die before the next. So next summer the adults die, and this is where the separate generations title came from. Also, let x1, x2, x3, etc., xn represent respectively the number of adult females in the first, at the beginning of the first, second, third, and nth breeding seasons. So x equal number of adult females. So with this in mind, we can now start building our mathematical model. But we also need one more thing, which is an assumption regarding the reproduction rate of the adults in this population. So let's first assume that this population has a constant reproduction rate. This is only our first assumption and will change as things get more interesting. Let's call this reproduction rate R. So what are we actually representing with R? Well, we're saying that each adult female, let's represent them like this, will produce on average R offspring, R female offspring, which will themselves survive to breed in the next breeding season. So what does this mean? Well, suppose that we have xn adult females currently. How much would xn plus 1 be? Well, it would be xn times R, since each female is producing on average R offspring. Okay? So this gives us the recurrence relation xn plus 1 equals xn times R. We can actually represent this recurrence relation in a different way as the change in population from one year to the next. So we can write it as delta xn equals xn plus 1 minus xn, and replacing xn plus 1 with its value from the formula that we have just got, this would give us xnr minus xn, which equals r minus 1 times xn. This formula will be useful for us later on. However, going back to the original form of xn plus 1 equals xn times r, we would like to find a solution to this. And by solution, I mean we would like to find any x, so it might be x4, it might be x100, x whatever. We want to be able to calculate it given only two things, r and the initial condition, which is x1, so the population in the first generation. So let's see if we can do that. Well, if we look at the equation, let's try to do some iteration on it first and see if we can get some pattern from it. So x2, starting from x2, we would get x2 equals x1 times r. x3 is equal to x2 times r, which in itself is equal to x1 times r, which would give us x1 times r squared. Now x4 would then be equal to x3 times r, which would be equal to, well, x3 is x1 times r squared, so x1 r squared times r, and we would get x1 r cubed. Now we can already see a pattern from this. As you can see, in the case of x2, r is to the power 1. In the case of x3, r is to the power 2. In the case of x4, r is to the power 3. So you can already guess the pattern that would give us xn equals, oops, let me clean that off. So xn would be equal to r to the power, well, 4 gave us 3, 2 gave us 1, so r is to the power n minus 1 times x1. And this is the solution to the equation. Taking another look at the equation that we have previously reached, xn plus 1 equals r to the n minus 1 times xn. From this equation we can clearly see that if r is greater than 1, x goes to infinity, and if r is less than 1, x decreases to 0. However, all of this analysis is based on the assumption that r is constant. But this is not generally the case. So usually r is dependent on x. Now, what do we mean by r being dependent on x? Well, let's assume that at one point the population in one animal species was very large. This would make the available food not enough to go around for everyone. and this in itself will make R decrease. So you can now see that R is not really constant. Now that we know that R is dependent on X, so R is a function of X, how would we represent this dependence? Well, one possible graph would be something like, say, here X is the x-axis and R is the y-axis, and the plot itself would look something like this. Now, we have some important points on this graph which would help us make some really cool conclusions. And these are the points at which R equals 1. Now, at R equals 1, the population simply reproduces itself. So every adult would produce one single offspring on average. So this means that the whole population will just replicate. So we would have the same amount of animals in the next generation that we did in the first generation. And this is why we call the points at R equals 1, we call them points of equilibrium. So let's call these points XA and XB. And these are points of equilibrium. Now, there are some important differences between XA and XB. At XB, you can see that if the population drops below XB, so anywhere between XB and XA, you can see that R becomes greater than 1. So take this point here, for example, you can see that R is greater than 1, which means that the population will now increase. However, if you take any point after XB, so if the population goes larger than XB, you can see that R then drops back to below 1, which means X will decrease. And this means that XB is a point of stable equilibrium. Now, unlike XB, XA has a different behavior. If the population drops below XA, R becomes less than 1. So take this point, for example, you can see that R is less than 1. And this means that the population will decrease when we drop below XA. And the opposite is true as well. So if the population grows beyond XA, R becomes greater than 1, and the population then increases, making XA a point of unstable equilibrium. Okay? Also, since when the population goes below XA, R becomes less than 1, this means that the population will actually keep on decreasing until it goes extinct, so until X becomes 0. And this means that you can think of going below XA as the point of no return for the population. Now, for clarity, let me redraw this graph somewhere here. So we would get same as before. The graph would look something like this. And we want to know more about the behavior of the population around the point of stable equilibrium, so XB. So let's draw XB again. And this is approximately XB. Now, By knowing more, I mean we want to know whether the population oscillates around xb, and if so, do the oscillations decrease in amplitude with time, or how does it actually behave? To do this, we need to use the famous linearizing assumption. Linearizing assumption, which tells us that we can assume that in small displacements around the point xb, we can assume that R behaves in a linear fashion. So what I will do is first let's specify the displacement from xb, or actually let's call it the departure from xb, and I will call it small x. Now what this allows us to do is, supposing this is a departure from xb, we can now write x as being equal to xb plus small x, and here small x can be either positive or negative if it goes in this direction. This in itself allows us to write r, which was a function of big X, we can now write it as a function of small x. And since we are considering the case of small departures, we can now, as we have previously stated, we can now draw R as a straight line with the same slope at the point xb, with the same slope as this graph. We can now get the equation of this line right here, and that would be R equals minus bx, where minus b is the slope of the line, plus, well, at the point x equals to 0, we know that from the graph R equals 1, so that would give us that the y-intercept is 1. So this is the equation of the line. What we can now do is we can now plug in the equation that we have just reached. We can plug it inside the original recurrence equation that we got at the beginning of the video, which is xn plus 1 equals rxn, if you remember. And this time we have to replace all the terms and write them as a function of the departure from xb. Now we already know that x is equal to xb plus small x, so we just have to replace the x's with this form, and whereas we replace r with the line equation. So xn plus 1 would become xb plus x small x n plus 1, which equals r is equal to minus bx plus 1 times xb plus small xn. And now we just develop this equation further. We get that xb plus xn plus 1 equals minus b xb xn, sorry, this should be xn, minus b xn squared plus xb plus small xn. Now xb and xb delete each other, and we are left with these three terms here. Now since we are considering small departures, so xn is small, this would make xn squared very small in comparison, and so we can ignore the term containing xn squared. What we get is xn plus 1 equals minus bxb xn plus xn, and this equals letting bxb equal a constant k, this equals xn times 1 minus k. and this is the final form. We can write this equation in a different form, as we did before, in terms of the change in population numbers from one year to the next. So delta xn would be equal to xn plus 1 minus xn, and substituting the value for xn plus 1 would give us delta xn is equal to minus k xn. Now this form here will help us analyze the behavior of the population around the point of equilibrium for different values of k. So let's start with the case. Let me separate this here. Let's start with the case where k is less than 0. So when k is less than 0, you can see that delta xn would be positive always, which would mean that the population would keep on increasing without limit. So x would increase till infinity, and this would be an unstable equilibrium. Okay, so let's now take the case where k is between 0 and 1. In this case, you can see that delta xn would actually keep getting smaller and smaller, and so the population will approach the equilibrium without oscillating. And so this is what we would call in engineering terminology a damped behavior. Now for the case where k is between 1 and 2, so k between 1 and 2, we actually need to do some iteration to figure out exactly what's going on with the population. So let's rewrite the equation for delta x, which is minus k xn, and let's assume that k is equal to 1.5. So let's also assume that at the first generation we had a value of x equals 1. And what would delta x be? Well, delta x would be minus 1.5 times 1, which would be minus 1.5. So what would x be for the second generation? Well, x would be equal to 1 minus 1.5. So x would be minus 0.5. So now we have a negative departure. Now, what would delta x now be? Well, since x is now minus 0.5, delta xn would now be positive, opposite to what it was before, and it would actually be a value of plus 0.75, giving at n equals 3 a value of x equals 0.25, which is again positive. Now you can see that x has dropped, then risen, and it will continue to do so if you do a few more calculations to check. So you can see that x is actually oscillating. However, these are oscillations with decreasing amplitudes. So first it went with an amplitude of minus 1.5, now it went with an amplitude of 0.75. So in absolute value, the amplitude is decreasing. So for the case where k is between 1 and 2, we get oscillations of decreasing amplitudes. So oscillations, decreasing amplitudes. And for the case of k greater than 2, if you do a similar analysis to the one that we just did with the iteration, you can see that you'll get oscillations of increasing amplitudes. It is also very important to note that all of these statements that we have mentioned are only valid for small departures. So for small values of x. Okay. One final thing to note is that if you compare the equation of the departure xn plus 1, which is equal to 1 minus k times xn, if you compare it with the recurrence relation that we have reached at the beginning of the video, which is xn plus 1 equals r xn, you'll remember that the solution to this equation was xn equals r to the power n minus 1 times x1. And by comparison, since these two equations are of the same form, you can directly figure out that the solution to this equation would be xn equals 1 minus k to the power n minus 1 times x1. And you can use this formula to check all of the ideas that we have discussed regarding the behavior of the population. This concludes our video. Thank you very much for watching, and consider subscribing and liking if you thought this was useful. See you all in the next one.